So far, we've seen a couple of ways to build lists, whether that's just by using generators or by using list comprehension to build up more complex lists based on some logical predicates. So, today what I'd like to do is go through some examples of how to manipulate lists. Generally in these cases we'll be using recursion because we want to iterate through the list, and while we don't have explicit loops, recursion will fill that role for us. So in each of these cases I'm going to use recursion to carry out some operation on the list. The first one that we have is count the occurrences of a given character in a string. So, for example, count the number of C's in a string, something like that. So let's do, that shouldn't be a capital C, remember that capitals are reserved for types. So, what will the type of this thing be? Well, it should take a character because that's what we're checking for. It should take a string because that's what we're checking in, and it should return an integer because that's the count of the number of occurrences. So I'm going to call the character C because I need to give it input for that, and then I'm going to define my base case. Now we saw in the first video where I introduced strings as lists, the base case for recursing through a list is normally the empty list. That's because that's the final element in every list. We see lists as a bunch of things stuck together and then eventually stuck into the empty list. In that sense, the empty list is the constructor for the type list. So my base case should be the empty list. And if I'm counting the occurrences of a character, there are no occurrences of a character in an empty list, so this should return 0. Now, we need to define what happens in the rest of this. So I'm going to give it a C, and I'm going to do the old trick where I say that I have something of the form x colon x's, and that allows me to pull x out and work with that value directly. Now, of course, you could define a function which takes the first element of a list out and then say that I want to work with, for example, a list y's. I could work with head of y's, which was the first element of the list, but pattern matching here allows me to sidestep any cumbersome function definition or application just by defining the list as by its shape. So one thing that we haven't seen so far, or considering the things we have seen so far, is pattern matching and guards as ways to define functions. Now we can combine these. So in the top level, the base case, I've defined the pattern of what happened when you have the empty list. Now I'm going on to pattern match on the case where I don't have an empty list, I have something const onto something else. And now I can use guards to define what should happen on that case. So I can combine these two ideas, allowing me to build up functionality. So the first case, let's think about it this way. The first case is what should happen if I encounter an element of type, or an occurrence of C. So that is to say, C is equal to X. So what happens here? Well, I should count. Let's think about a simple case. I'll write it up here. If we have a list that looks like this, then if we take that element X out of the list, then I will be left with the empty list. But I should count that if it's equal to C. So when it gets to the empty list, it will return a 0. So I can just add 1 to the overall integer that we're returning. So every time I encounter an element of the list that is equal to C, I can just add 1 to the function because I know that the function, when supplied with arguments, will result in an integer type. So it's perfectly valid for me to add integers to integers. So what do I mean? Well, I mean that I can write 1 plus count car, and I need to give this a C. I've checked the element X, so I then move on to X's. So this thing here, when it's supplied with arguments, will result in this type because this is the output type of the function. So I can add 1 to any valid integer, and this function will be a valid integer when it's applied to arguments. The next case is when C is not equal to X. Now, of course, I could define this as C is not equal to X, or I could use the otherwise keyword. I'm going to do that. Otherwise, I should not count X as an occurrence of C. So I don't add 1, but I still recurse. Okay, so the recursion here, again, is just applying all of this logic that we've defined over here. So I'm saying, okay, if we're empty, then we're at 0. We should count 0 occurrences. Otherwise, if C is equal to an element of the list X, or the string X, I count that by adding 1 to the overall total. If I'm in the case where that has not happened, C is not equal to X, I don't count, but I keep going. And I remove the first element of the list to ensure that I'm moving towards the base case. So I'm always going towards the empty list. So let's save this. And let's load in, and I've called this manipulating lists. Oop, that's a main function, we don't want that just yet. So if I load this in and I call this, and let's see, I call C in Clemens. Oh, I should make that a lowercase c, because I'm giving it a lowercase c to work with. I get a count of 1. And if I add more c's here, then I get the count for them. So we can see that this function works. So let's move on to the next one. So write a function which will return the second last element of a list of integers. Now that's a little bit trickier. We need to think about the case when I have the last two elements of a list. Either way, I'm told to return the second last element of a list of integers. So I'll call it but last, and then it's going to take a list of integers. So let's call that int. Well, we'll get a choice on what we call that. And it's also going to return the second last element, which is going to be an int. So how do I do this? Well, in this case, I need to think about the case where I should return a value. The case where I return a value is when there are only two elements left in a list. So if I have an x and a y, where y is the final element, I return x. Now you might think this should be something complicated or difficult, but in Haskell, I can just define that case directly. This is the power of pattern matching. It allows me to just say, okay, if you encounter a list that looks like this, then just return x. Okay, so that's a very simple way to do this. And then I need to define how I'm going to work towards that case. So I'm going to do but last, and I'm going to do the usual x colon x's, and I'm going to say but last on x's. And that's my function defined. I could define the empty list, but I shouldn't ever reach that case if this function works appropriately. I mean, it would be absolutely valid for me, but I shouldn't reach it because this case should cover that for me. However, the editor is going to be upset and saying, oh, it doesn't include this one, but my function ends before I reach that case. If I reach that case, then I wouldn't be doing this function properly because I should never encounter it. But let's just take a little look at what's happening. I just tell the Haskell to look for the case where you have two elements left in a list and return the first one of those. Otherwise, you just keep working until you reach this case. So let's save, and let's call but last. And it's a list of integers, so let's say 1, 2, 5, and this should return 4 for me. Oh, actually no, I haven't reloaded my file, so I should do that first. And now it returns 4 for me. Of course, I could do this with any length of list, and it returns 49. And you can see, even though I'm getting a warning about non-exhaustive pattern matching, I know that I'm not going to reach the case that the IDE is worried about, so I'm not defining that. If I wanted to make it happy, I could do that. Again, it's a case that would never be reached though, so I'm not going to worry about it right now. If you want to, if it makes you feel better to get rid of the yellow underlines, you can of course define the case of the empty list, and that would be fine. So let's move on to the next one. We're going to write a function which will reverse a given string. Now this is going to involve an operator that I haven't shown you explicitly, but you know about it from other programming languages, which is the concatenate operator, which looks like this. If I define the type, it's something that takes a list, another list, and returns a list. This just joins two lists of the same type. That's all it does. You've seen this in other programming languages, so it's nothing to worry about here, but we will need it for this one. So let's say we call it not capital I, my rev, and it's going to take a list, or a string, sorry, which is of course a list, and return a string. So what happens in this function? Well, in this case, I do have to care about the empty list. I'm going to work case by case. So I'm just going to say this returns the empty list. And then I'm going to say, if I have the empty list, this should return the empty list. And then I'm going to say what happens when I'm in the case x colon x's. You might be wondering why I always call this x colon x's. This is the Haskell convention for pattern matching on lists where you don't have to care about the specific front type. For example, if I was working with tuples, I could spell out the tuple here, but I'm just dealing with one element at a time, so I don't need to worry about that. So what happens here? Well, the way I could think about this is if I find an element at the front, that goes to the back. Okay? And then I check the rest of the list. And I keep just putting them to the back, 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 until we reach an empty list. So the way that I'm going to do that is instead of putting my recursive call afterwards, I'm going to put it at the front. And we'll see how this works in a second. So I'm going to do my rev on x's, and then I need to somehow stick this element x, which was at the front, to the back of the list. So how will I do that? Well, I'm going to use the concatenation operator. That's no fluke that I introduced that earlier. So I'm going to add x to the end of the list. Now one problem is x is an element of a list. In this case, it's a character. So I can't just add that directly because this needs something of the type list. What I can do is just stick x in a pair of brackets, and then Haskell will recognize this as a list. So let's save that. Let's reload, if I remember to this time, and do my rev, and let's say we give it a string called string. So this should reverse this list, and there you go. You can see that it's taken the elements at the front, moved them to the end, and we get the reversed list that way. So that's a fairly straightforward way to carry this out. Hopefully this makes sense to you. You don't have to do the recursive call always in this case where you do 1 plus something else. It can be something a little bit more complex. You just need to think about what should happen to each element of the list and try not to make it any more complicated than it has to be. Okay, so now we have a function, write a function which checks if a given string is a palindrome returning a boolean. So we return true if it's a palindrome, where a palindrome is a string that is the same forwards as it is backwards. So we have a myRev function which will be very useful for this. So we'll call it isPalin, and it's going to take a string and return a bool. Oh, that's sting, not string. So let's see how we do this. So we have a list. I'm just going to say x's. I could check every element of the list against the final element of the list if I was so inclined. But what I'm going to do is I'm going to say x's equals my rev x's. And that's all I need to do. Now you might be worried about why I'm using this double equals operator on strings. I've taught you many times, for those of you that I've spoken to in Java classes, that when you use strings, they're passed by reference, and therefore you should use dot equals, because if you use this the double equals sign, you'll actually be comparing the pointer to that string. Now Haskell doesn't work that way. Haskell has an implementation of the double equals for every type that it works on. So it has a special implementation on strings that checks element by element. So you don't need to worry about that in this language. So let's save and let's test out isPalin. So let's say race car, which is a palindrome, and it should return true. Indeed I do. If I do race car 1, that's obviously not a palindrome because I've just stuck a 1 on the end of what was a palindrome. I get false. So I can use this double equal just to compare lists directly because of the way that Haskell works. We'll see this later on and how this works with functions like double equals. But for the moment, all you need to know is you can use this to compare string types in Haskell. So that one's a fairly straightforward solution. Let's look at something that's a bit more complicated. So here we have write a function which will flatten a list of integers returning, or flatten a list of lists returning a list of integers. So how do I do this? So it's going to take a list of lists. Now how do we define that type, or how do we declare that type in the type level, you might be wondering. Well, I know that a list of ints looks like this, and so a list of these things should look like this. So again, it's very simple for me to specify a list of lists in Haskell. I just put more square brackets around the thing I'm interested in. And this will go to a list of ints. So again, I want to think about the cases and what I do in each of those cases in order to flatten the list that I'm working with. Well, I'm going to have an empty list, and in that case, I probably want to return the empty list. This is a general pattern. Sometimes it's not always what you want to do, but this time I'm returning a list, so I need to use the list constructor at some point. So if you're working with something where you take a list and return a list, it's quite likely that you're going to need a base case where the empty list is equal to the empty list, just so that you can put the constructor in there somewhere. Now, we're going to have another case where I have something of the form x's colon x's, and something will have to happen here. Now I'm using this format because if you're reading my Haskell code, then if you know the conventions, you know immediately that this is something, this x is at the front, is something that's of the form list. And you know that this thing here is a list of lists. So we're taking the first element out, and then we're just returning it, or we're going to do something to manipulate it, and giving it back a flattened list. So what will I do? Well, I know that x's is a type list, and I know that I have an operator here which will join elements of lists together. So I can just say x's plus plus flatten x's. So what this is going to do is it's going to take out the first list, and it's going to take out every element or every list within the list of lists and concatenate them all together, eventually concatenating into the empty list. So this should reduce my large list down to something more manageable. So let's look at that. So we're going to have to write something to give this a list of lists. So let's say we have list 1, 2, 3, and then we're just going to say 2 lists for the sake of ease, and let's say 4, 5. So if I've done this properly, I should return the list 1, 2, 3, 4, 5. And there you go. So I've found a way to flatten a large data type down into a smaller one, and it's really quite straightforward. In fact, if you look back, all of these functions are quite short because Haskell allows us to write very succinct, very clear and clean code. This is one of the many benefits of using Haskell over an imperative language. There are, of course, cases where you would prefer an imperative language, but here you can see we've put a lot of thought into very short lines of code. So I would recommend that you spend some time understanding how each of these functions work. We'll have more examples of functions and some exercises for you to tackle as we go along, of course, but it's very important that you understand how these functions work. I hope you found this useful. Of course, if you have any questions about anything I've covered today, please do let me know. Thanks.